Massachusetts. Before we start, please note that today's slides are available under the Handouts tab. We'll also have a Q&A at the end of the webinar, in addition to instructions to claim NAVCEP Continuing Ed credits. As we go through the webinar, please feel free to enter your questions in the box on your screen. And finally, per usual, we'll be sending a recording of this webinar to all registrants later this week. Today we have two speakers telling the story of the King Open project. First, we'll hear from Shannon Kaplan of AKF Group, Renewable Energy Designers. And second, we will hear from Brett Henning, U.S. Product Manager at SMA America. Linked here is a short video documenting the development of the King Open School project. We would have loved to have played this for you today, but in practice we found that the audio and video did not come through very well in this webinar. But I do highly encourage you to take some time at your convenience. You get a chance to hear from the stakeholders and get some great mid-construction shots of the school here in the video. And one more thing before we begin today, on the next slide. We are thrilled to announce that Civic Solar is now a part of the CED Greentech family. Greentech is the nation's leading solar distributor, offering unmatched scale and project support. We look forward to partnering with you on the design, engineering, and procurement of your next residential or commercial project. And without further delay, I'd like to introduce you to our first speaker, Shannon Kaplan from the AKF Group, who will speak to the context and goals of the King Open School project. Shannon, over to you.
Great, thanks, Connor. So just to give you a starting point, I wanted to talk a little bit about how this project came about and why it had some of the goals that it had. The King Open project is a lower school and middle school project in the city of Cambridge, Massachusetts. The project was handed out with some really lofty goals. One of those was to achieve a LEED Gold rating under LEED BD+C for schools. The project actually ended up during design deciding to go for LEED Platinum because we felt that we were in such great shape that there was no reason not to go for something higher. The project was also aiming to achieve, originally the goal was to hit net zero energy, but realistically, given constraints on the site, the target became to achieve a minimum of 60% of the annual energy generation on site. The city of Cambridge has been working carefully towards having a higher number of net zero energy building stock, and they've been doing a lot of lessons learned on these projects. They did build a previous school called the MLK school, which hit a target of 50% on-site annual energy generation. So they wanted to push this project a step further, thus the target at 60%. They also wanted to make sure that all of the generation was happening on the actual project site. There were discussions about the fact that there's a park next to this project and would locating some solar panels on the parkland be an acceptable strategy, and it was decided that no, the goal was to measure this within the building site and to capture within the building site because that's where the energy was being used. The city of Cambridge is actually on quite a mission for net zero. They have actually passed a citywide goal to achieve net zero emissions by 2040. And part of this goal, they've recognized that buildings need to be energy efficient. So they've actually passed a law that starting in the year of 2019, which we're in right now, all buildings built for the city, which would include all of these schools that are part of the school district, would need to go as far as they could towards being net zero. Now, this project was started prior to the 2019 goal coming into place, but they knew it was coming. They had already started with the MLK project, so they wanted this school to see how close it could get to net zero energy. As we took a look at the project site, you can see here the green area marks out the total project site area for this building. This school site is located in the middle of a neighborhood. You can see there's a lot of small residential buildings, some smaller businesses in the area. So this is by far one of the largest buildings in this whole region, and there's a park off to the south. The school program, which you can kind of see through the light green here, included a west building, which was home to the lower school and middle school programs, as well as an east building that houses the shared gymnasiums, the cafeteria space, and this building also serves some public community functions. So there is a public library on the north end. There is an outdoor public pool, and the Cambridge Public School System's offices are also located in that east building. So this programming goes beyond that just of a simple school. If we took a look at what we thought this building would be used based on this building configuration and the usage hours for all of those different programs, we did run an energy model where we were trying to target what we thought was as close to a real predicted energy use. And using that as our baseline, we're trying to determine how close to net zero we could get. So you'll see that we predicted the annual energy use to be about 2.2 million kWh per year, and that we did an analysis of what would happen if we just filled the entire site with PV panels. We found that if we were able to do that and just build a massive wing of PV over the site, that we would be able to generate more than twice the annual energy. So we felt really good at the starting point. However, there's always challenges. We then took a look at just the available roof area. So that's now this blue outline. And we found that there was significantly less of the roof area available. Some other things that we came up against on this project was we talked about whether we wanted to put PV off of the roof, but there were some constraints here. You have to remember this is a school. Some of the open space is needed for children's play, and we didn't feel that it would really evoke the feeling that they wanted for these children to be constantly playing underneath this solar panel canopy. So we did not want to put any panels over those locations. We also did not want to put any over the pool because one of the great things about the pool is having the sunlight beating down on you to let you get really hot before you jump in. So we didn't want to go with it there. To the south of this east building where the pool is, you'll also see that what looks like some basketball courts, and they are basketball courts. So there was a concern about putting panels too close to those courts. So we didn't want to constantly have basketballs hitting and damaging the PV panels. And that park to the south actually also has some baseball diamonds. So there was also some concerns about using any of the walkways. So overall, the city decided that they really did want to stick with only having solar panels on the building form itself. We did our analysis of what we could fit, including all of the required walkways for code, perimeter walkways, roof hatch access. Most of the mechanical systems on this roof were put into sunken-in mechanical wells that we could put PV panels over top of. And by doing that analysis, we actually determined that the roof itself would be able to generate 54.5% of the energy. But remember, our target for this was that 60%. This is just a shot to give you a sense of the building form in 3D. So you can see that though those roofs do look like they're big flat areas when we look at that site plan, there are some articulations to the roof here, which has impacted the amount of panels that we could put on the roof. But we also needed to balance that with the architecture, the needs for the building in other ways. So it wasn't that we were just able to say all flat roofs everywhere. You can also see in this shot where some of those sunken mechanical wells are, and here they've already started installing the structural railings to support those PV panels floating over those areas. We also have a rendering of the building that shows how the PV panels were intended to be laid out. This gives you some insight to the strategies that we used for mounting and racking those panels. All of these roofs, with the exception of the library, which is to the upper right corner of this image, have a flat roof scenario. So we were going with a self-ballasted east-west orientation racking system. When we did our preliminary layouts, we found that we could actually improve the density of PV panels by going with the east-west layout and minimizing the amount of space that had to be removed for panels due to self-shading from panel to panel. And that overall, the losses that we were seeing on a per panel basis for energy generation were exceeded by the additional number of panels that we could put on. And since our goal here was to maximize the amount of energy generation per square foot of roof area, because that was our limiting factor, that this installation in this orientation was actually the most optimal that we could get to get the most energy generation. That roof over the library is a single flat but tilted surface, so we were able to go with a simple flat installation along that roof, as well as with those connecting hallways that you can see connecting the west and the east buildings. In order to overcome our deficit on the energy generation, we looked at some other strategies for how we could add additional panels to the building without breaking that rule of not going off the building. We took a careful look at the west building, and we're able to find that we could put some PV panels over a series of the windows on the eastern and southern facade. The building's orientation on site looks to be due north-south. However, the site itself is at a slight angle. So the eastern facade is actually angled slightly south of east, and the southern facade is slightly west of south. So we were able to get enough energy generation out of those panels, as well as capitalize on the fact that they could be a shading feature for the windows to help manage some of the daylight and heat gains during the summer months. In addition to those panels along the facade at the windows, we found some other locations where we could mount panels vertically to the sides of the building and use them as a form of cladding and get some extra energy generation there as well. At this point in our calculations, we were now predicting that we were going to get to that 60.2, which exceeded our target just a little bit. I will say we were carrying a slight energy contingency in there. So this we felt would give us a comfortable buffer based on our predicted energy usage and what we thought that we'd be able to generate from this PV system. One of the other challenges that we faced on this was with putting all of these panels on the building, we also needed to determine the location for the inverters. Several ideas were thrown out in early design phase. Nobody wanted to go with the central large inverters. There was a lot of risk there that if one inverter went down, we would lose a significant portion of our production. Nobody could think of a good location for it on site. And in general, this idea was vetoed early on. Another idea that had a lot of great discussion around it was going to the microinverters. However, the school district was not ready to deal with that level of maintenance that could happen with that many microinverters, considering the significant number of panels that we had on the project, and there were a lot of other challenges that presented. So at the end of the day, we decided to stick with the tried and true string inverters for this project. When we took a look at the string inverters and the number that we would need for this layout, we ended up realizing that there were going to be a lot of them. The project wanted to have these located on the roof. They didn't want to set aside the space in the building nor deal with the heat that would come from the inverters being located in the building. We also had to be really aware that we needed to make sure that these inverters were tucked away in places where they could be easy to access for any needed maintenance, and also be within the roof enough that we wouldn't need to provide any fall protection or anything like that in order to have people get access to them. So we had to think carefully how to group these. We were tucking them into some of those mechanical wells and finding other spaces along walls or different locations that we could try and group these. And we were trying to create as few groups as possible so that the electrician wouldn't be forced to run around the building roof to all these different locations and memorize all these locations just to get to all of the inverters. In our initial design, we were looking at a number of smaller string inverters. We were trying to use inverters that would convert straight to three-phase power, since this is a three-phase building. And our original design ended up calling for 58 small string inverters, which was quite a challenge to locate on that roof. However, one of the things that we talked to the owner about at the beginning of this project was how quickly things are always changing in this industry, and that we wanted to have a chance at the time when we were doing the final bid on and award on the project to reevaluate where the technology stood at that moment in time. There had definitely been some changes from when we started this design back in 2015 to when we started our construction phase. Among those were that the panels themselves had actually improved in efficiency. So we went from a basis of design on a SunPreme 370 watt panel to a basis of design on the SunPreme 380, which helped us further get that to that 60% target that, we got a little bit more over top of that target just from making that change. But there was also some improvements in the inverter technology, including the ability for us to have small roof-mounted inverters that actually were able to carry a larger load per inverter. So we were able to, within that, working with CD Tech on that final design, get the total number of required string inverters down to just 22. And this also allowed us to then group these into just 4 locations on the roof, which makes it much easier for the school to maintain and deal with as an ongoing basis.
All right, thank you, Shannon. That was fantastic. And thank you for bringing a sense of place and for laying out the goals for this project. Now I'll pass the mic to Brett Henning of SMA America to tell us more about their Sunny Tri-Power Core 1 lineup of products and how they helped us realize the ambitions for this project.
Yes, thank you very much, Connor, and thank you, Shannon, for that great introduction to the King Open School project. And it's going to be my pleasure to dive into a little more detail about our Sunny Tri-Power Core 1 commercial inverter solution and some of the supporting technologies and services that SMA offers to put together a complete commercial PV system solution for projects like King Open School. Go ahead and roll it one more time, Connor. All right, we'll get this working. Good deal. So King Open School project, Shannon gave a great introduction. I think she touched on a lot of what their considerations were in terms of selecting an inverter from what their power production needs were, logistical challenges in locating the PV inverters and the arrays, the demands for flexible design. Given the different rooftops and the east-west orientation that they had. I think what we're going to present here, we're going to show that how they came around to the Core 1 inverter is we've developed a solution that provides for or addresses a lot of these needs. Some of the key solutions and features that I'm going to be talking about today, just kind of a summary here. First is the inverter itself, a three-phase commercial inverter, a fully integrated solution for faster installation, comes in multiple power classes to give you some design flexibility and scalability. We've got built-in technology to ensure that you get maximum harvest from your PV array, including our new SMA Shade Fix technology, which is string level optimization technology. We've got best-in-class safety features that are required for commercial systems, whether they be rooftops or carports or other areas, as mandated by National Electric Code. And lastly, we've got services to support the lifetime operation of the system and ensure that the O&M and service doesn't become a burden and a problem for the system over its life. So let's start with the inverter itself and its most obvious difference when compared to other competing inverters in the commercial space is the Core 1 comes as a fully integrated ready to go solution out of the box. Basically all your installation crews need to do is unpack the inverter, stand it up, and they're ready to start connecting the PV strings and the AC lines and commission the inverter. When you compare that to other commercial inverters that are out there, they're typically delivered as multiple components, 2 to 3 different components that have to be assembled on site. And not only that, but then you need to construct racking structures in order to place those inverters. None of that is necessary with our Core 1 inverter, which saves you installation time and cost as you're putting your system together. And next, something that Shannon delved into in quite detail was, the critical nature of energy production and ensuring that you get maximum production you can get from the system, and you get the energy, you get the production that you expect when the system is actually installed. Couple of key features that deliver that in the Core 1 are, first, the inverter is designed with 6 independent maximum power point trackers. So that means you can connect 12 strings up to these 6 different MPPT trackers, and each one of those MPPT trackers will determine the maximum power point for the strings that are connected to it. This gives you the flexibility if the roof demands that you have different string lengths in different sections of the roof, or in the case of east-west arrays like they have at King Open School, you can connect those strings to different MPPT inputs on the inverter, and you'll be sure that you're getting the maximum power from each of those sections at whatever time of day. Secondly, built into the inverter is our shade fix MPPT algorithm. This is an intelligent MPPT tracking algorithm that basically is able to determine the maximum power point even under partially shaded conditions. So for any string of the array is partially shaded by HVAC or other equipment, the inverter is smart enough to find the maximum power point for those strings, and again, ensure that you're getting the maximum power that can be harvested from the array. And then lastly, with each of those MPPT trackers, we've got intelligent string monitoring. So we're monitoring the current and voltage on each of those inputs, and we're able to compare the inputs to ensure that if one input starts to perform less than it should relative to the others, we're able to send event messages that make you aware that the system is potentially underperforming and needs to be addressed. All of this comes built into the inverter, so you're getting the maximum harvest you can possibly get in detailed array monitoring without having to add the cost of optimizers in the array. And Shannon talked about the decision here with being such a large system, not wanting to have micro inverters or even optimizers on every panel that had to be managed and monitored. Next slide. Next, we talk about design flexibility and scalability. So in addition to each inverter having those 6 MPPT inputs, the inverters also come in 3 different power classes to fit different size projects or different size subarrays on the same project. First, we've got the highest power model, the 62.5 kilowatt Core 1, which is going to be your most economical solution for large projects with very uniform arrays. The 62.5 might sound like an odd power size. We came up with that because basically with that number, 16 inverters equals exactly a megawatt. And where you have interconnection limitations or incentive programs that require an exact megawatt or capped at an exact megawatt size project, you're able to use this inverters. Again, 16 inverters is exactly 1 megawatt. Then we've got the 50 kilowatt model, which is also for medium to large scale commercial projects. You've got 20 inverters per megawatt with that model. And then we go all the way down to the 33.3 kilowatt model, which is a more economical version for smaller projects or even larger projects where the arrays are segmented and you need a smaller power inverter to address individual subarrays. So this is a good fit for carport type projects where you've got a smaller subarray format. The other key niche that the 33 kilowatt is targeted at, and I won't go into it in detail here, but for retrofitting or repowering legacy PV systems with 600 volt stringing and 600 volt arrays. There's a whole hour-long presentation that could be gone into on that, but this is our model to address that opportunity, which we're seeing more and more of these days. And finally, when you're selecting an inverter, you want to know that the inverter has the proper certifications and listings and is approved for installation wherever your project is. We've got the Core 1 certified to all the product standards required for North America, including the UL 1741 here in the US and the corresponding Canadian standard in Canada, and various interconnection listings across the country from California to Hawaii, New York, and even down in Puerto Rico. The Core 1 is approved and ready to go, which means you've got no barriers, no restrictions when you select our inverter, getting your projects approved, permitted, and finalized. So let's talk about safety for a minute. I want to talk about we consider the best-in-class safety features that we've built into the Core 1 inverter. When we look at commercial projects, there are some key safety concerns that you have. Go ahead and roll the screen, Michael. Thank you. So, there are, of course, safety is a concern because we're building PV systems in commercial environments. They're on occupied buildings, they're in public spaces like parking lots and things like that. So safety is a real concern. And of course, there are codes. The National Electric Code establishes certain requirements that have to be met and complied with to meet those safety needs. So you really don't, with a project like the King Open School, it says here, 0 safety compromises. It's not something we want to pay lip service to. At SMA, we're committed to ensuring that the solutions we provide are the safest and at the same time the most reliable solutions that you can use in a commercial environment. I'm going to talk about 2 key features related to safety that we're providing in the Core 1. The first being our solution for the module level rapid shutdown that's required in NEC 2017. And second is the arc fault protection, or AFCI, that's built into the inverter. So let's start with module level rapid shutdown. The solution we've developed is based on an industry standard that we worked with SunSpec and other participants in the solar industry to develop a standard for communication between the inverter and the array to implement module level rapid shutdown. And it's really a very simple solution. Essentially, we have integrated into the Core 1 inverter a transmitter that sends out a standardized keep alive signal that is defined by a new SunSpec standard. So anytime the inverter is running, is powered, it will be sending out this signal over the PV lines. That signal's carried over the PV string conductors, so there's no need for additional wires or even wireless communications to carry this signal into the array and to the individual modules in the array. And then within the array, you have module level devices, like shown on the left here, that are essentially listening for that keep alive signal. If the inverter is up and running and it's sending that signal, then the devices receive that signal and they allow the energy from the modules and the array to flow through to the inverter. But if the PV system is shut down, in the case of, for instance, an emergency response, the PV system is shut down, the inverter's powered down, they stop sending out that signal. Now the module level device is not receiving that signal. Basically disconnect the modules each from the string so that you de-energize the array to the levels required by NEC. So what you end up with is especially for commercial scale systems like the King Open School, a very cost-effective solution for implementing and complying with the module level shutdown requirement in 2017 NEC. By integrating the transmitting capability into the inverter, it ensures that you have a reliable, trouble-free operation. You have no additional wiring to install, no buttons to install, no external transmitter that has to be installed, no power wiring to additional equipment that needs to be installed. So it's almost just like installing a normal PV system, and you get this capability. This is a feature that SMA was active in the development of that SunSpec standard. We were the first to market with a commercial scale solution, and we feel we have the best-in-class solution to ensure that you're providing the safety that your project needs for first responders and complying with the National Electric Code. Let's look at the next safety feature, AFCI, or arc fault protection or arc fault circuit interruption. This is a feature that hasn't received as much attention as rapid shutdown, but it could, from some perspective, be almost as important or even more important than rapid shutdown, because what AFCI is doing is detecting faults in the PV array that could potentially create a fire situation or a fire hazard. And it's been a requirement in PV systems going back to 2011 NEC, and it was expanded further in 2014 NEC, and of course remains there in 2017 and 2020 NEC. But what's been a recent development is that a new standard or product standard has been published by UL. It is UL 1699B for certifying products that provide this capability. Prior to having this standard, products were certified to what was known as an outline of investigation, kind of a rough draft of a standard, if you will, that was originally drafted in 2011. So in August of last year, 2018, they finally completed a fully developed, fully documented standard for certifying products to AFCI. And some of the key things that were enhanced in the standard over the outline of investigation were that products need to be tested in a test setup that more realistically simulates the PV array characteristics. They also took great pains to ensure that the test procedure was reproducible. So from test lab to test lab, or wherever you test your products, if you follow the standard procedure, you should get reproducible results. And lastly, of course, what they wanted to ensure was that we were able to get reliable arc detection and interruption and make sure that we prevented additional fire hazards to the best ability, and also that we had resistance to nuisance tripping so that the system still operated reliably and didn't trip under situations where there really wasn't a fault. SMA with the Sunny Tri-Power Core 1 was the first and still, we believe, the only commercial inverter certified to this new standard. So with the Core 1, you get improved safety, reliable system operation that you can't get with any other product. Let's step forward to monitoring and control needs for PV systems. You install a PV system, you need to be able to monitor it and make sure that it's performing to expectation. Again, going back to what Shannon presented and the importance of the energy production offsetting the usage in this facility. You need to know that the system, after it's been installed and over the life of the system, is actually producing what it should. And when there are issues, you need to be able to narrow down and identify where those issues are and address them very directly. So that calls for a monitoring solution that can be integrated across the entire project and bring all the data together onto a monitoring platform where it can be intelligently used to ensure the performance of the system. From SMA, we have essentially a three-tiered solution for monitoring PV systems. It starts with the SMA Data Manager controller. So this is an on-site data logger communication gateway. So it goes on the project site, and all the inverters are connected to this device, and this becomes your gateway to seeing what's going on in the system. The second tier is our SMA Sunny Portal, which is our no-cost web-based monitoring platform that has been recently enhanced to provide you the visibility you need to see how your system is performing. And lastly, everything is underscored or undergirded by our new ennexOS cross-sector energy management platform. So this is our software solution for managing the new distributed energy resource world of devices of both distributed generation and customer consumption. Start with a little bit more on the data manager. So again, this is your on-site hardware device that is going to be communicating with and collecting all the data from the different inverters at the site. So the inverters are connected to this device through a local area network over Ethernet cables. And the data manager then has not only the smarts to be able to collect data from the inverters, but it also has built-in software intelligence to be able to implement local control capabilities like zero net export or reactive power control, if those are required for your project. The data manager then acts as your gateway to the World Wide Web, where the information can be shared and pushed up to either our Sunny Portal monitoring platform, or if preferred that you use a third-party monitoring platform, we support industry standard communication protocols like SunSpec Modbus to support third-party monitoring platforms as well. And then looking at our Sunny Portal monitoring platform. I'll step to the next one. Thanks. So Sunny Portal has been a monitoring platform that SMA has been offering free of charge for over a decade now, with many thousands of registered systems worldwide. We've recently completely redesigned and enhanced the platform. One thing we haven't changed is that it is still no cost to systems that are built with SMA inverters and our data manager device. By registering your system in this platform, you're able to get enhanced capabilities like inverter performance comparisons, performance ratio calculations, detailed data analysis of your system performance, as well as proactive notifications of system performance issues. All this, again, I can't emphasize enough, comes at no charge to you. So whether you, even if you do have a third-party monitoring service, you can still also monitor your system in Sunny Portal and get all the features that we provide at no additional cost. And then this leads us into service and O&M support for the life of the system. So once the system is installed, again, you want to be sure that the system performs as expected, as the customer is expecting, to ensure that you have customer satisfaction and that you're meeting the energy generation and goals of your project. SMA offers a couple of solutions specific to the Core 1 that ensure that your system can remain operating reliably, and also that it doesn't become an overbearing burden to your installation operations to maintain these systems and keep them operating and ensure that they have the system uptime and the generation that you're expecting. I'll touch on a couple of key features. Want to roll to the next one? So the first thing, when we were bringing the SMA to market, or actually even when we were in the conceptual development phases of the SMA Core 1 inverter, and we talked to customers, what we heard very clearly was that the traditional approach to servicing string inverters, of replacing inverters, was particularly challenging in commercial inverters where the inverters are located on the rooftop, or in carport systems where they're usually located high up off the ground and underneath the carport canopy. Getting the inverter, doing an inverter swap in that situation requires getting heavy lift equipment to the site, scheduling around the operations of the building, obviously the school day for a school like King Open School, or a retail operation having to schedule around their hours of operation. Getting that heavy lift equipment in place, the manpower to operate it, and getting the failed inverter off the roof and a new inverter on the roof is extremely challenging and costly. In addition to, again, costing more to do, you're also extending the downtime while you're trying to schedule all this. The system, that inverter may be offline, so you're extending the downtime of the project. What we did with Core 1, taking that input, is we designed the Core 1 to be able to do board level servicing, or what we call board level exchanges, which means through our Sunny Portal monitoring, our service line department can diagnose the component of an inverter that has failed, and we can send a replacement for that part only. And then the installer's technicians, with some online training that SMA provides, can take that part to the roof where the to the inverter and replace only that part and restore the inverter to full operation without the need for heavy lift equipment or additional manpower, or again, scheduling around building operations to get heavy lift equipment into the site. So this is a significant reduction in both the cost and the time to repair a failed inverter. And then building on that, kind of bring it all together in a new service that we call SMA Smart Connected. And what we're doing here is this is basically proactive system monitoring by our SMA service line. So talked about registering the systems in Sunny Portal, which is of no cost to you. This service is also no cost. So if you register your systems in Sunny Portal, you sign up for this Smart Connected service, and once you've done that, the SMA service line personnel will monitor the event messages and the performance of your system. And they will take the action to notify you when there is a performance issue with the system, whether it's something that has to do with the array, like an AFCI fault, or a loss of grid connection that might be a circuit breaker that is tripped for the inverter. Or if it is in fact something that indicates a failed inverter, we will go ahead and proactively start the shipment of the needed replacement part for that automatically. So that saves you the trouble of having to have your own eyes on every system and checking every system to make sure that it's working. And it also saves you an initial truck roll to go out and troubleshoot and diagnose an issue when one comes up. So SMA's already done that diagnosis. Again, if it's an inverter failure situation, we've already started the replacement part coming to you. That part arrives and you can go out and replace it. So this is a huge cost savings, a huge burden savings to you after the project has been installed, but yet you can still ensure that your customer system is performing and that they're going to be satisfied with the production of the system. And I think that wraps up my presentation. I'll just kind of summarize and say again, the highlights here with the Sunny Tri-Power Core 1, product that offers the flexibility and scalability that you need for a variety of commercial projects and portfolios, fast and efficient installation, maximum energy harvest without any added cost or complexity associated with optimizers or microinverters. We've got the best-in-class safety features that you're going to find in a commercial inverter. And we offer monitoring and service solutions, mostly at no additional cost, to ensure optimal performance for the life of the system.
Fantastic. Thanks, Brett. That was a really fantastic dive into the Core 1 lineup and its capabilities as it pertains to this project and beyond. As a reminder, all that great content can be found in the Handouts tab right now on your control panel. And of course, we'll be sending out a copy or a recording of this webinar later this week. Before we jump into a couple questions, just a quick reminder, for NABCEP continuing ed credits, please email michael@civicsolar.com with NABCEP in the subject line. Brett, since we have you here, let's throw a couple to you first. One of the big questions that came up here was, what's the difference between the Dash 40 and the Dash 41 lineup of products?
Good question. So yeah, the original Core 1 inverter that we launched in end of 2017 was the STP or 50 kilowatt Dash 40 inverter. The key difference between that and the Dash 41s, which we launched about a year ago, there's two key differences. First, the Dash 40 only came in the 50 kilowatt model. With the Dash 41s, we introduced the 62.5 kilowatt model, higher power model for higher watt peak modules and larger projects, and the 33 kilowatt model for, again, your smaller projects. So we've added some additional power classes to give a little additional design flexibility. And in the Dash 41, we have implemented those new safety features that I talked about. So while the Dash 40 did have AFCI functionality, it was in the Dash 41 that we certified that the new AFCI functionality to the new UL 1699B standard. And it is also in the Dash 41 that we have implemented the SunSpec compliant rapid shutdown transmitter. So the Dash 41 is the product line that we have now. The 50 is, for the most part, no longer available. I think we may have a few left in stock that we're still selling off. But basically, the Dash 41 is our product carrying forward, additional power classes, and additional safety features. Those are the highlights.
Excellent. Thank you. One more for you, Brett. This one might require some spelunking to the data sheet, but do you happen to know offhand, someone asked the maximum slope that a Core 1 can be installed on? That's a tough one.
Yeah, that does require, as you said, spelunking into the actual installation manual. I do know that it is in the installation manual. You know, it is designed for installation on a flat roof or on a flat surface. So I think it might be somewhere in the 3 to 5 degree range, which most flat roofs will slope in that area. If you have something like a slanted roof that has a more steeper tilt, then you might need to construct a platform for it to sit on.
Excellent. And are there any other mounting alternatives for the Core 1 lineup?
There are, and we've seen a lot of I'll say innovation by installers. We've seen a lot of installations of Core 1 in carports, and of course carports are very structurally unique in terms of, you know, who's built the carport. So there's not one standard solution for a carport solution. Rather, we've seen various different engineered solutions depending on the actual structure of the carport. And we've also seen a lot of mounting solutions for ground mounts, whether they be mounted on the back of a fixed tilt array, or in cases where it's single axis tracker arrays, we often see the inverters mounted basically on the top of the driven posts that are also used for the array mounting. So yeah, we have seen a lot of different solutions, and our application engineering team at SMA can supply you with some examples of solutions so that your engineering team can figure out what the best solution for their given project is.
That's perfect. Thank you. And as a reminder, for any questions we do not get to today, Michael's contact information is on this slide, and mine will be on the next slide. So please don't hesitate to reach out to us. One or two questions for Shannon before we close out today. Shannon, first, question was, on a municipal school project like this, how involved was the city and what was that process like?
Sure. So for this particular project, the city was very involved. They are actually technically the owner of the building in this instance. So it's not, the building does not belong to the school district. It actually belongs to the city. Therefore, we had to go through the city's procurement process, which meant that we were going through state procurement. And this was of particular interest on this project when it came to the photovoltaic system, because we were looking for panels that would perform at a certain level, as well as the inverter products as well. So we did have some discussions with them in terms of the procurement process and the ability to rate a more closed specification for the project. And they were able to get an exemption from the standard state procurement process for just one of those key components, not for both. But that did help us out in terms of going for that really high performing goal for the energy generation on this project.
Excellent. And that actually leads us to another question someone had of, was the payback period calculated on this project, and what did that look like?
That is a great question. We did look at paybacks of various aspects of this project, but at the end of the day, that was not the deciding factor for this project. The city has this much more important public agenda that they're pursuing. And when we looked at the payback for the photovoltaic system versus some of the other items, such as the geothermal well system that's installed on this project, the solar payback was actually pretty decent. I know that the solar payback has come under some scrutiny recently, since a lot of those incentive programs have taken away that kind of free dollars towards your system. But overall, it was somewhere in the 15 to 20 year range, I believe. So it was under the expected life expectancy of all of the parts that were installed on the project.
Excellent. Thank you, Shannon. All right, folks. Well, with that, we've concluded our scheduled programming for the day. Thank you so much for joining us. We hope you learned a little bit more about both the development of this project as well as the SMA commercial inverter lineup. Please do reach out with any questions, and we look forward to hearing from you soon to assist you with your next solar project. Thank you so much.